Now, since we talked about the more basic points of black holes and kind of the introduction on what we're going to be talking about here in the presentation, I'd like to talk about more about the misconceptions many people have on black holes. So, a black hole, although unstoppable, does not take in all matter. The matter it does take in is relative to the size and what is around its surroundings. So many people ask the question, what if the Earth was revolving around a black hole? So, if the Earth was revolving a black hole the size of the Sun, the Earth would continue rotating around it just as normal, although life on Earth as a human would be much different without the Sun. That lets us move on to our next point, which is, can the Sun turn into a black hole? The obvious reaction is no, although it contradicts popular belief that it is impossible for the Sun to turn into a black hole because of its core. The core for the Sun would have to be around 3 times as larger than it already is for the surface of the Sun to implode on itself and give in and turn into a black hole. So this goes on to our next point, sizes of black holes and what they're capable of. When taking in more energy, holes become larger, and that means they're capable of more. This is known as the stellar mass black hole. Of course, these black holes first have to be a neutron star to turn into a stellar mass black hole. And that is what is currently in the center of our galaxy right now. This one was first found and has been measured several times. It is found to be 3.5 million times larger than the Sun. This leads many astronomers to believe that there are other black holes at the center of other galaxies, considering space is so large, it is hard to explore all these galaxies and figure out what really is at the center of them. I know one thought that came up in my mind when I was exploring this topic is, what is it like to be in a black hole? Besides obviously dying right away when sucked into a black hole, there are many things that actually happen throughout that process. Black holes move incredibly fast, faster than any speed on Earth, approximately 299,792,458 meters per second, which is the speed of light. This is because you are no longer connected to any kind of surface that travels at its own speed. You are part of the black hole now. The word may sound funny, but the actual term for what happens to your body inside of a black hole is called spaghettification. This is a term that NASA coined, and it refers to the drastic stretching horizontally and vertically that the body goes through inside of a black hole, if one were to go into one. The spaghettification shows that the body sees time as going much slower than on Earth originally. This also works hand in hand to the black hole's specific gravitational field that is much different to its outside surroundings. The gravitational field has its very own unique tidal forces. Tidal forces are secondary effects of a gravitational field. This gives the illusion of time slowing much quicker and the body stretching erratically. What may be even more nerve-wracking is before your body dies, it goes through severe trauma and it will never be the same again. But after you die, what exactly happens to your body? And that's what many astronomers is what exactly happens to the matter that is sucked into the black hole. More broadly, the question is the kinds of matter absorbed by a black hole. One question is, why isn't there any light? Force of gravity in the black hole is so immense and continues to grow after more mass is included, light has absolutely no room to escape from it. Gravity and its relationship to mass have a great role in this as well. The more gravity an object in space has, usually corresponds with the amount of mass it has, and vice versa. After speaking about stellar mass black holes, you can see how that corresponds. Next is the radius. As stated before, the size of what black holes take in leads to a mass millions of times larger than the Sun, but somehow it still remains to have a radius smaller than Earth's. This is started from the compression the black hole has from the very first explosion it creates. The radius is usually very accurate when measuring a black hole because that is one of the only spots astronomers can look at and distinctively make a measurement, because you can notice where the matter is all being absorbed. It is very difficult to spot a black hole without first observing material around it. The black hole shows no light, no noticeable wave differences, and moves at a speed of light. But if from very far observational distances, astronomers can spot where this material is being absorbed and taken away from space. We're now going to take all the concepts that we previously talked about in the first 2/3 of the video and kind of tie it into where in the black hole it's taking place, how it connects to other parts of the black hole, and just kind of tie all the events together into one. So the three layers are outer event horizon, inner event horizon, and singularity. The two event horizons can be classified together. The event horizons are known as the points of no return. That is where all the matter is being sucked into place. As we talked about earlier, no light escapes from black holes, and that's why they are considered black holes. That's because once the matter goes in, there's not even room for light to escape. That is the outer event horizon, where you kind of see the outer edges, where astronomers have to look back from very far. The inner event is where the radius is. It's not technically inside of it yet, but it is the inner, where the exact matter is being pushed in. And as I'm stating again and again, gravity of the black hole is very attractive and can be seen as its very own. Finally, we get to the singularity. Right here is a perfect kind of graph of exactly how a black hole looks like. So right here is the singularity. It is inevitable that the matter that travels through a black hole ends up at the bottom of it. This is just regular physics, but the more mass you place into a small volume of space, the stronger the gravitational pull gets. What this means is when the matter gets from the outside and goes in and in and in, past the event horizon, past all of this, and gets down to the singularity, the stronger this gravitational pull gets and keeps it there as forever, pretty much. So then that takes us to the Schwarzschild radius. The Schwarzschild radius is pretty much any rotating or non-charged mass that is smaller than the actual radius of what it is in. We can also tie in things that we talked about earlier in the video, like how if you were a person that got sucked into the black hole, your time would distort and be much slower than it is. Right here, before you get to the singularity, is the gravitational space-time distortion. In the quiet region, negligible gravitational influence is right over here, and that depends on how large the black hole is, how much the mass is leading up to it, and if the mass is actually decreasing, which we're going to talk about right now. So the reason black holes function the way they do is from classical mechanics of physics. This is because matter is not escaping. This all has to do with one another. However, quantum mechanics is quite different in the way it is the opposite reaction for the black hole. So the basic principle is that every particle has an antiparticle with the same mass and opposite electric charge. When these two particles meet, they try to annihilate each other. The reason this is important is, what if these two particles meet at the point of an event horizon right before they are about to go into the black hole? So So what astronomers think could be happening is if this process happens right at the reach of the event horizon, one of the particles can reject one another, and this could affect in kind of a rupture. The reason this is important is that this could cause a decay in the black hole. Although there are very large, significant black holes in our universe, there are much smaller black holes that are also significant but are usually forgotten about. Astronomers connect these quantum mechanics with these smaller black holes, thinking that it might have been larger at one point and then shrunken down over time. However, this is not a very explored topic, and because it is so controversial, it still has to be explored more until there is 100% conclusion on the matter. Black holes are incredibly complex, and it even shows you that the most skilled professional astronomers in the world and over history can't put 100% conclusion on every single fact that comes out about them. That wraps it up for my video this semester. I had a great time exploring the topic, and I think I learned a lot throughout this entire course. These are my sources, and thank you for watching, and I hope everybody learns something, and I can't wait to see every other person's presentations as well. Thank you.